Okay, in this video I'm going to show table 6.2 from Peleus, and I hope you can read this on the video. But basically this does a great job of summarizing typical characteristics for our lasers and LEDs. Okay, so first of all we have spectral width, and for the LED it's typically 20 to 100 nanometers wide. Whereas for laser diodes with multiple modes, 1 to 5 nanometers, and single mode laser diodes, less than 0.2 nanometers. So the single mode lasers are the ones we really prefer. Rise time is measured in nanoseconds, and for LEDs it's in the range of hundreds, a couple hundred nanoseconds. But for laser diodes and single mode lasers, it's down to much less than something like 1/10 of a nanosecond. So not only are lasers much more spectrally pure, much narrower line widths, but they're also much faster. Okay, the modulation bandwidths are correspondingly much higher. In megahertz, less than 300 megahertz for the LED, but 2,000 for the laser diode and 6,000 for the single mode laser. And these numbers are basically just inversely proportional to the spectral widths. Okay, coupling efficiencies. This is the coupling efficiency into fiber. LEDs have a poor coupling efficiency because they tend to have a large cone. Laser diodes are better at coupling, and single mode lasers are even better. The compatible fiber types include, for LEDs, multi-mode step index and multi-mode grin. So basically this is why that coupling efficiency is so low for the LEDs, because they have a very wide, they have a very large cone coming out, and so they're only appropriate for coupling into multi-mode lasers with very high numerical apertures. With laser diodes, it's a much smaller numerical aperture on the output, and so we can couple into single mode fibers in the laser diodes. Temperature sensitivity, well, I drew that curve for the laser diode, and the response function of output optical power versus drive current really does depend a lot on temperature, and so basically laser diodes need to be temperature stabilized, whereas LEDs don't. The type of circuitry to drive them, well, it's more complicated for laser diodes, in part because of the temperature stabilization that's needed. Okay, the lifetime, they're all lasting a long time, 10,000 hours, so they last many years of use, and as you might expect, there's a trade-off on cost and performance. The lower performance LEDs cost less than the higher performance laser diodes. To get a single mode laser diode, it costs more. And then corresponding to the modulation bandwidths, LEDs have low modulation bandwidth, so they're appropriate for short distances or moderate distances and moderate data rates, whereas laser diodes are appropriate for very long distances and higher data rates. Single mode lasers give us the best modulation bandwidth, and therefore are appropriate for the longest distances and the highest data rates. Okay, so this is a real nice summary table showing you the characteristics of diode light sources. And this is complementary to the table that I mentioned earlier, or that I sort of reproduced earlier in my slide, and I'll show it here, which is table 6.1, and it's giving these wavelength ranges. And so this tells us which material systems we're going to use for our 1550 nanometer, for instance, which will be the indium gallium arsenide phosphide layer. One final topic in lasers is, I'll show you this figure 6.3. This is a surface emitting LED. Okay, this is one where the geometry is different from what I showed in my previous slides. In my previous slides I showed this type of geometry where we have a multiple heterojunction stack, and we have an active region which is emitting. Where's the picture of it in the book? Here, I can't seem to find it. Okay, well here it is. Here's our more typical structure. We have this multiple heterojunction stack, a bunch of different types of semiconductor layers. We have our active layer in between two confinement layers with a higher refractive index, and then we have our electrode, which causes confinement in the lateral direction. So we only have gain in this part of the medium. And so this is an edge emitting device. Surface emitting devices, turns out, are very cheap to manufacture. We can make very low cost surface emitting LEDs this way, where we've taken part of the surface of the device, etched it away, and made a place for a fiber to go. And this can turn into a very high coupling efficiency and very low cost devices that are already fiber coupled and don't need to have anything fancy going on. No lenses are needed because we're butting the fiber directly up against this active layer almost. And so these are surface emitting LEDs, and they're a big thing in datacom applications where we have surface emitting. Well, we can make surface emitting lasers as well. Okay, I'll stop here. Thank you.